Okay, let's talk about Module 25. This module is all about epoxides, which, in case you don't remember, epoxides are a form of cyclic ether. They are cyclic ethers where you have a three-membered ring with two carbons and an oxygen. Those are your epoxides. So they are a little different than your typical cyclic ether, but we can make them in the same way. So I'm going to start by just talking about how we can make cyclic ethers. So here's an example where I've got a molecule that's got an alcohol at one end and it's got an alkyl halide at the other end. You might remember that when I add this reagent NaH, this is a very strong base, and this is going to remove the most acidic proton. So in this case, the most acidic proton is going to be the one on the oxygen. So I'm going to deprotonate the alcohol. That gives me an alkoxide, which is a good nucleophile. And when I have a good nucleophile and I have an alkyl halide in the same molecule, I can do an intramolecular SN2 reaction. And that's going to give me a 1, 2, 3, 4, 5-membered ring. So again, this is an intramolecular SN2. And it gives me a 5-membered ring. Might as well just extend my arrow up here because I've made my product. So I get this cyclic ether in this case, and then Br minus is a side product. Hydrogen gas would be a side product of the first step, but this is a way I can make a cyclic ether. In this case, it's a 5-membered ring. This second example is just, I don't know, to show something a little fancier, but it's the same idea. Again, I have NaH, which really is just going to be a source of H minus, strong base. That's going to deprotonate the alcohol. And that gives me an alkoxide again and an alkyl halide in the same molecule. And again, I can do this intramolecular SN2. It might be a little clearer if I draw this in a chair form. Not my greatest chair ever, but I'll take it. So I have the alkoxide up here. I have the alkyl halide over here. This probably wouldn't happen in the chair conformation. This would probably flip up into a boat conformation for the reaction to happen. So it might flip up something more like this, where I have the oxygen here and the bromine here. And I can do this SN2 reaction. So that's going to give me a product that looks like this. So it's a bicyclic ether, or I could draw the product like this. So a couple examples there of how I can form a cyclic ether using an alkyl halide, an alcohol, and NaH. So you might ask, can I do this to form an epoxide? And I can. I may not have used this term, but halohydrin is another word for a vicinal halo alcohol. And if I have the alcohol and the alkyl halide on neighboring carbons, this is a way I can make epoxides. So you may remember that you can form this halohydrin or this vicinal halo alcohol by reacting an alkene with Br2 and H2O. I'd invite you to pause right now and practice drawing that mechanism, especially if you haven't done it in a while. So pause, draw this mechanism, and then come back. Hopefully you paused and now you're back. Hopefully you tried this mechanism. Remember, when we react an alkene with a halogen, we're going to start by having the pi bond attack sigma star BR. Right, so pi CC attacks sigma star BR. At the same time, we're also going to have our counterattack where the bromine lone pair is going to attack pi star CC. And that's going to form our bromonium ion intermediate. It's always a good idea to practice old mechanisms. And then my second step is going to be where my water attacks the more substituted carbon of the bromonium ion and breaks that bromonium ion open. That's going to invert the stereochemistry at the carbon that gets attacked. So in fact, the way I've drawn it, oops, that bond is now broken. There's a methyl group here. The way I've drawn it, I'm going to get the enantiomer of this product shown over here. But that's why we have the plus minus to say we're going to form both enantiomers. So my first choice was to make the bromonium ion coming forward. That's going to end up with the enantiomer of the product shown. My last step would be I have a very acidic proton, so I'm going to call Sol to come and remove that. So that gives the enantiomer of that product. So that's how we form a halohydrin. It's relevant to review the reactivity of the bromonium ion here because notice a bromonium ion is a three-membered ring like an epoxide is. So that's going to remind us some of the things we're dealing with when we attack a three-membered ring. All right, so that's an old mechanism. Now, when I take my halohydrin and I add sodium hydride, again, sodium hydride is really just a source of this strong hydride base that is going to deprotonate the alcohol. And when I deprotonate the alcohol, it has a leaving group next door. It's going to do an intramolecular SN2 to make the epoxide. And we get bromide as our side product there. Notice stereochemistry here turns out to be important because remember this intramolecular SN2 needs to happen via a backside attack. If I were to try to do this with this halohydrin, notice the one I've used up here looked like this. Again, drawing chairs is one of those skills that you should practice regularly. And this oxygen lone pair is lined up for a backside attack on sigma star CBr, right? Sigma star CBr would be here. So that's an easy alignment, and that can happen in a pretty straightforward way. If I imagine the halohydrogen at the bottom here, practice for yourself drawing a chair for this one. Now I would have my alkoxide here, my bromine there in the equatorial position. Now sigma star CBr is way over here. And there's no way for this to happen. So this would not make an epoxide. So in order to form the epoxide, we need to have access for the oxygen lone pair to be able to reach sigma star CBr. That's the point there. So one way to form an epoxide is an intramolecular SN2, just like we could do with larger cyclic ethers. Intramolecular SN2 is an option. It's not necessarily the most convenient option. So chemists are always looking for, can I find a better way to do this? And it turns out we have found a better way. It's going to take advantage of a class of compounds with a relatively unstable oxygen-oxygen bond. So we've seen before with alkenes where we can react an alkene with HBr and peroxides that have this OO single bond. So this would be a peroxide. And we saw that this OO bond is relatively weak. And that gives us some advantages in how it's going to react. Those peroxides tend to form radicals very easily. They tend to be very reactive. In fact, if you have an old bottle of ether and it's developed some peroxides by oxidizing in the air, it can become explosive. So generally, these molecules with OO bonds, we want to be careful with them. But there is a class of them called peroxycarboxylic acids or peracids that have an OO bond sort of shoved into the carboxylic acid functional group. Many of these are unstable. One that is relatively stable and therefore gets used a lot is called MCPBA, metachloroperoxybenzoic acid. So that's this one. So generally, that's the most common one that gets used. And it's going to take advantage of that OO bond to add an oxygen to an alkene. Okay, so these are used to convert alkenes into epoxides. Notice here, I start with an alkene, I end with an epoxide. So I'm gonna start by drawing my mechanism down at the bottom. This is my preferred way to draw this mechanism because I like to think about donor-acceptor interactions. Generally, we think of in an alkene pi cc as being our donor orbital, and if I asked what orbital is pi cc most likely to donate into, pi cc is going to be most likely to donate into sigma star OO. All right. One thing I'm going to do before I draw this mechanism actually is it looks a lot cleaner if I actually first draw an alternate resonance structure for the peroxy acid. So I could imagine, as a first step, thinking about resonance here. And I have a lone pair next to a pi bond, so I could redraw this peroxy acid in an alternate resonance structure. You might ask, why would I do that? That's not the most stable resonance structure. That is true, but it is the resonance structure that is going to make the mechanism easier to visualize. So that's why I'm going to use it. So when I think about how this reaction happens, I have my pi CC as a donor. What's the LUMO of this other molecule? Well, you might say pi star CO. It's true, but pi CC is not going to be able to donate directly to pi star CO here. There is another orbital that is also a very good acceptor and is acting on a relatively weak bond, and that's going to be sigma star OO. Two very electronegative atoms bonded to each other. So my first arrow is going to be pi CC donating to sigma star OO. That's going to break the OO bond. Okay. Now at the same time, I now have in my molecule here, there's going to be an intramolecular hydrogen bond that already exists between oxygen and hydrogen. So this here is an intramolecular hydrogen bond. That old Gen Chem concept that comes up so much in biology also comes up a lot in organic chemistry. So I have a hydrogen bond there. And I'm going to take that hydrogen bond to the extreme. I'm going to have the oxygen lone pair grab that hydrogen. Now, how is the oxygen lone pair going to grab that hydrogen? It is going to have oxygen lone pair donating to sigma star OH. All right. That makes sense. We've seen that happen a million times before, where an oxygen lone pair grabs an acidic hydrogen. And at the same time, I'm going to have a third arrow, where the oxygen lone pair on this oxygen, similar to the reaction where we form a bromonium ion. When we have a form of bromonium ion, pi CC attacks sigma star BRBR, while the bromine lone pair attacks pi star CC. Same thing is going to happen here. My oxygen lone pair is going to donate to pi star CC. So very complicated in terms of donor-acceptor interactions. And each one of those donor-acceptor interactions is something we've seen before. So none of them are super exotic. It is analogous to that bromonium ion formation mechanism, but it does look a little strange. That is the way I like to think of this reaction happening. I will say that if you ask anyone else, they would give you a mechanism that has a greater, what I would call, economy of arrows. And that greater economy of arrows looks like this. It would have the pi bond attack the oxygen. They would have this bond flip over here. They would have this double bond flip down here to grab the hydrogen. And then they would have the OH bond go and do the attack. So my mechanism was a total of 2 arrows for resonance and then 5 arrows for the reaction. Their mechanism is only 4 arrows total. It gets the job done, but I think it's a little harder to understand those arrows. But that's the accepted mechanism for this reaction. So if you take a future course and they ask you to draw a mechanism for epoxidation using MCPBA, that's the one I would go with. All right. So using one of these peracids, we can create epoxides in a single step from alkenes, which, all right, that's a convenient thing to have in our pocket. I'm going to pause there, and then in a minute I will pick up what we can do with epoxides. So we've talked about how we make epoxides. Now we're going to talk about what we can do with them.